After the advent of superconductivity, till now so many theories has been proposed to explain this phenomenon. Actually, a number of theories which have been proposed to explain the phenomenon of superconductivity have varying success. For example, the first theory which was proposed is called classical theory, and this is just based on the free electron theory of metals. But this theory is very limited. But in this lecture, we will see about the classical theory or classical explanation of superconductivity. But apart from this, due to the so many drawbacks of this theory, several theories in history has been proposed. For example, you will see a phenomenological theory by London and London. In 1935, this theory was proposed. And after that, in 1950, a semi-phenomenological theory was proposed by Ginsberg and Landau. Okay, but this theory is also not very successful. Actually, finally, we find a very successful theory in 1957 by three scientists called Bardeen, Cooper, and Schrieffer. Actually, this theory is the most successful theory which accounts for the most of the properties of superconductivity, and popularly this theory is called B.Sc theory. Okay. So actually this B.Sc theory is a microscopic theory, and this theory actually is the most successful one and explains all the properties of superconductors except those with high critical temperature ceramic superconductor, that is the superconductors at high temperature. Only those cannot be explained by this theory, but the low temperature superconductivity is clearly explained by the B.Sc theory. Okay. In fact, these three scientists were awarded Nobel Prize in 1972 for his work. Okay. But as I have told you, the aim of this present very short lecture is to provide you the classical theory, or you can simply say the classical explanation of superconductivity. This is a very short explanation and you know it. But before that, I would like to just give again you some of the facts regarding the superconductivity which you have already learned in my previous videos. You know, superconductivity is the phenomenon in which electric current passes through a material without any resistance. Okay. You also know that when materials are classified on the basis of electrical conductivity or electrical resistivity, it is categorized in three categories: insulators, semiconductors, and conductors. You must remember that superconductors are not a class of materials. Actually, superconductivity is a state of material. A conductor may behave like a superconductor, even an insulator, even a semiconductor, even an alloy may behave as a superconductor. Actually, this is a phase, this is a state when the resistance becomes almost negligible. Okay, so it is not a particular type of material. In fact, in superconducting state, you know that resistance becomes almost negligible, or you can say zero, and so the current flows without any resistance. In fact, as we have learned earlier in my introductory lecture and several other lectures, that this superconducting state of the material is observed below a temperature which is called transition temperature or critical temperature, and it is denoted by the symbol Tc. It means when temperature of the material is less than Tc, then the material behaves like a superconductor and it is in the superconducting state. But when temperature of the same material is greater than Tc, the material is completely in its normal state. Okay? No superconducting behavior is found when temperature is greater than Tc. And actually, this Tc has different value for different materials. In fact, a large number of metallic elements and alloys have been found to exhibit superconductivity when its temperature is lowered below the critical temperature for that. Okay, and this critical temperature, as I have told you, is different for different materials. Okay. You have also learnt in my previous video that the transition of a superconducting state is actually a second order phase transition. When this transition is governed only by temperature, not by magnetic field, then transition from normal state of a material to its superconducting state, or transition of superconducting state into a normal state, that is a second order phase transition. Okay, and the temperature at which this transition takes place, that is called transition temperature or critical temperature, denoted by the symbol Tc. And when T is greater than Tc, it means temperature of the material is above or greater than the critical temperature, then the properties of the metals are completely normal. Okay, but when T is less than Tc, then superconducting properties are displayed. And the most important or most dramatic superconducting property is what? That is the absence of any measurable DC electrical resistance. So when the temperature is lowered than Tc, then the material is transformed into superconducting state, and several properties of that material is actually changed. And among those properties, the most important property is the electrical resistance, which almost vanishes below this temperature Tc. Okay. Actually, I have till now talked about this superconducting transition at the critical temperature only in absence of this absence of the magnetic field. But it is found that this critical temperature is a function of magnetic field. When the material is placed in a magnetic field and then you will lower its temperature, then its critical temperature is not same as that was in absence of magnetic field. So we simply say that the transition temperature Tc is a function of magnetic field H. It means that transition temperature Tc is magnetic field dependent. Actually, it is found that in presence of the magnetic field, the value of critical temperature is lowered. It means, let us suppose, if Tc is equal to 4.2 Kelvin for some material in absence of magnetic field, when H is equal to 0, then Tc will be less than 4.2 Kelvin when H is not equal to 0. Okay, it means in the presence of magnetic field, the value of this critical temperature is decreased. Okay. In fact, in presence of magnetic field, another very important phenomenon also takes place. As you have already studied in detail, and just now I have told you that when H is equal to 0 and the material transits from the superconducting state to the normal state. This is the superconducting state and this is the normal state. And there is a transition from superconducting state to normal state or normal state to superconducting state at temperature Tc. Then this phase transition is a second order phase transition. But in presence of magnetic field, if such phenomenon takes place, there is a transition from normal state to superconducting state or superconducting state to normal state. Then that is not a second order phase transition. That will be just a first order phase transition. So this is a very remarkable fact that in absence of magnetic field, transition of superconducting state to normal state or normal state to superconducting state is a second order phase transition. But when magnetic field is present, then such a transition is not a second order phase transition, but that is a first order phase transition. Okay. So these were some of the facts which you have already studied earlier in my different videos. As I have told you earlier that from today we are going to start the basic theories for explaining the superconductivity. Before this we have learnt about the experimental survey, experimental results and different observations. Now it is time to talk about the theoretical aspect of superconductivity. And in this regard, as I have told you earlier, that there are several theories which has been developed time to explain the superconductivity. But among all those theories, the most important, most significant and most successful theory is called B.Sc theory, which we will learn in our previous video, in our forthcoming videos in very detail. Okay. But in this present lecture, our aim is to explain this superconductivity by the classical theory or you will see the classical explanation of this superconductivity. Okay. And as I have told you that our free electron theory of metals gives us a pathway to explain the superconductivity to some extent. You know that when we have studied free electron theory of metals, particularly the Sommerfeld's theory, then you have discussed the conductivity of metals, okay, on the basis of Sommerfeld's theory. And you have learned that the conductivity of metals on the basis of free electron theory of metals or Sommerfeld's theory is given by Ne square tau divided by m. This sigma is the electrical conductivity of metals. Okay. And you know the electrical resistivity rho is 1 over sigma. Okay. So rho will be given by m over Ne square tau. Okay. You have already learned this formula earlier in free electron theory of metals. Okay. So this is the expression for the resistivity of the metals. Okay. And in this expression, you know, m is mass of the electron. Okay. E is charge of the electron, and this n represents the concentration of free electrons in the specimen. When you say concentration of free electrons, what that means? That means the number of free electrons per unit volume. And what is this tau? This tau is known as relaxation time. And you know what is this relaxation time? This is actually the time taken by the electron between two successive collisions. When actually electrons are drifted inside the metallic surface, it suffers collision with the lattice. Okay. And time taken between two successive collisions are actually different. And when you will take the average or mean of all those free times, that is called relaxation time. So this is defined simply as the average time taken between two two successive collisions. Okay. So resistivity is given by that formula. Now you can see from this result that this resistivity is actually inversely proportional to this tau. Because for a particular metal, for a given metal, this N will be constant. M and E both are universal constant because these are mass and charge of electron. And N depends on the material. So for a particular metal, this N will have also a constant value. But this tau, which is called relaxation time, that depends on temperature. Tau is temperature dependent. And that's why this rho is temperature dependent. And you can see that this rho is inversely proportional to tau. Okay. Now let us see what will happen or how this tau will be affected when temperature will be decreased. In fact, when temperature decreases, then vibration of lattice will decrease in the crystal. Okay. At higher temperature, the vibration is more violent, but as the temperature decreases, the lattice vibration decreases. And if the lattice vibration will decrease, then the probability of electron-lattice collision will also decrease. Okay? Because lattice is now slowly vibrating, and so the collision between electron and lattice will also decrease. And when the collision will decrease, it means frequency of collision decreases. Okay. So when you say collision decreases, it means now collision is taking place at larger interval of time. Okay. And when collision will take place at larger interval of time, what does it mean? It means tau increases. So finally you can say that with decrease in temperature, the relaxation time tau increases. Why increases? You have learned. Because the decrease in temperature leads to decrease the lattice vibration, and this decrease in lattice vibration decreases the value of electron-lattice collision. And due to this, there will be an increase in relaxation time tau. Okay. So if temperature is decreased and now say that temperature is decreased and it now tends to 0 Kelvin. Then classically when temperature will almost 0 Kelvin, our specimen is at absolute 0. The vibration is completely stopped classically. So according to classical theory, then there will be no collision of electron. And if there will be no collision, what will be tau? We will actually wait for a collision, but there will be no collision. So we simply say that when collision will be stopped at 0 Kelvin temperature, this tau will become infinite. Okay. So when temperature T tends to 0 Kelvin, then the relaxation time tends to infinity. Okay. And if tau becomes infinity, and you see here that rho is inversely proportional to tau, so when tau will become infinity, rho will become 0. So definitely when temperature of the metal will approach 0 Kelvin, then relaxation time will approach infinity, and so that this resistivity of the metal will tend to 0. And if resistivity is 0, resistance will be 0, and the material or the specimen will offer no resistance in the flow of current through it. And this is the phenomenon of superconductivity. So why on decreasing temperature the material behaves like a superconductor, I think it is clear to you on the basis of this classical theory. In nutshell, you can say when temperature is decreased, then actually the electron lattice collision decreases, relaxation time increases, and when temperature is extremely low, almost 0 Kelvin, then relaxation time is almost infinite. And if relaxation time is infinite, then resistivity will become almost 0. And so the material now exhibits superconductivity. In fact, what happens actually, you can see that when the temperature is lowered below a particular temperature which is called transition temperature Tc, then actually among all the free electrons, some of the free electrons now behave differently. You know, in metals there are free electrons which takes part in conduction, okay? But when temperature is lower than this Tc, then some of the free electrons behave differently. And actually those electrons which behave differently are called superconducting electrons. So when temperature T is less than Tc, then the specimen contains two types of electrons. One is called super electron and another is called normal electron. And these super electrons are those electrons which do not suffer any scattering, which do not suffer any collision. And if they do not suffer any collision, for those electrons, the relaxation time will be infinite and resistivity will be 0. So actually, a fraction of electrons which become superconducting in the sense that they have infinite relaxation time below the temperature T equal to Tc. And these electrons undergo no scattering, and it is these electrons which are responsible for superconductivity. Okay. So I think now it is clear to you how we can explain this superconductivity on the basis of classical theory, or you can say on the basis of free electron theory of metals. Okay. But you can see, although the above explanation appears very convincing, you can think that it appears that this is a correct theory, and if it is correct, it will be able to explain all the facts regarding the superconductivity. But a story is something different. Actually, on the idea which has been used to explain the superconductivity in free electron on the basis of free electron theory of metals, if these ideas are utilized to explain the properties of superconductors, then it badly fails in explaining most of the properties of superconductors. Okay. So this is not a very accepted theory, or not a successful theory, you can say. In fact, as I have told you earlier, that the most appropriate theory and most successful theory of superconductivity is a quantum mechanical microscopic theory, and that is popularly known as BCS theory. And in our forthcoming lecture, actually we will see the details of the BCS theory. First of all, we will see the qualitative explanation of this BCS theory without any calculation. But after that, we will also see the quantitative concept of BCS theory. On the basis of appropriate calculation, we will learn about BCS theory. Okay. So thank you very much.